The last two functions, promise. Beyond this, no more functions. So exponential and logarithmic functions. We had interesting applications before about the concentration of a medicine in a patient's bloodstream. We had we modeled the height of infants between birth and 60 months with a square root function. We modeled
the height of a ball.
The height of the ball, the trajectory, excellent, with a quadratic function. These two functions have even more interesting applications, in my opinion. For example, bacteria populations like bats, fish, rats, mice, whatever, rabbits, they all follow an exponential function. When we take a turkey out of the oven and we put it on the table to cool down, its temperature is decreasing using the log function. When there is an earthquake, the earthquake's intensity is measured with the logarithmic function. The radioactive decay, the radioactive substances decrease their mass in time using an exponential function. So wide applicability in the real life situation. So we'll start with exponential. We will graph the function. We will use transformations. We'll look at some applications, and then we'll continue with the log functions. We're going to be able to, we will add these two functions to the list of functions: linear, quadratic, square root, rational, blah, 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 blah. We're adding these two functions there. And also we're going to be able to solve equations for these two functions and look at those applications. That's the entire chapter. So we're going to look at the exponential function, then the log, graph, and some transformations to understand what is happening here. Then we will look at equations and some properties of log, equations, exponential and log, and word problems. That will be the entire chapter. Okay. So let's start with exponential. This is 4.1. Exponential functions. Why do you think they're called exponential? Can I remove this? Yes, I can. Why do you think they're called exponential? The exponent is the variable. That's why. So here is a, which is a given number, and x is the variable. So a is the base. Given number. It's just a simple number. Here's a question for you before we look at different options. Do you remember when we graphed x squared? And when we graph negative x squared? Two shapes here as well. Okay, so we have to be careful. So let me ask you a quick question. 3 quick questions. Can I raise 0 to the 4? I meant 0. I don't know what that is. Yeah, something grew out of it. Okay, so can I take 0 to the 4th power? The answer is 0. Of course I can. 0 times 0 times 0 times 0. Of course. What about 1 to the 3rd power? Yes. And what about, let's say, negative 2 to the 3rd power? What do I get? Negative 8. Very good. So all these numbers are fine when it comes to thinking about them, simplifying, whatever. However, they're not allowed as bases for the exponential function. So what is allowed? The exponential function can be either strictly greater than 1, not 1. The base of the exponential function cannot be 1. And the other possibility or option is when the base is smaller than 1, between 0 and 1, but not negative and not 0. So the base cannot be 0, 1, or negative. And in case you're asking me why, I'll give you the answer why. There is only one explanation. this function will not exist if we allow the exponential function to have base 0, 1, and negative. And of course, I'll divulge already. This is the inverse of this. This is the inverse of that. So if this function accepts 1, 0, or negative 2, or a negative number as the base, this function cannot be defined anymore. So that's the only reason. All these are allowed. They exist. I can determine them. I have answers for them. But they cannot be the base of the exponential function. Yes, please. Yes. Thank you. No, every now and then I look just to make sure, and I rebooted the whole system because I just want to make sure that the other 4 videos are gone. Yes, I am. Thank you. Okay, so obviously, we're going to have a shape for this and a shape for that, like we had for x squared and negative x squared. Totally different shapes. Okay, so let's look at an example of this. Let's say f of x equals 2 to the x, and you see the base is greater than 1. And let's look at an example of this, a simple one. Let's say 1/2 to the x. Okay? So we are looking at f of x equals 2 to the x. And of course, we start always, we want to graph 2 to the x. And we have to start with always, we start with the what? We start with the domain. The domain of this function is all real numbers. It's a friendly function like polynomial functions. It's not the same, of course, but I call it friendly because I never have to worry about its domain. It's always defined on everything. I'm going to pick a few numbers, small ones. Are you okay? -2, -1, 0, 1, and 2. And accordingly, we have to determine the y coordinates. When I plug in this function, when I make x equals -2, I get 2 raised to -2, which is 1 over 2 to the second power, which is 1 over 4. So the first answer, the first y coordinate is 1/4. For -2 is 1/4. Can anyone give us what happens at -1? Very good. Can anyone tell us what happens at 0? Careful. Let's write this. 1. Let's write this aside, please. I'll come back. This is very important. A raised to 0 is always 1 unless A is 0. So A cannot be 0. 0 raised to 0 is not 1. It's an Why do I say one thing and I write something else?
It's a Monday.
Do not write the IN. Indeterminate case. And this is in Calc 1. So 0 raised to 0 is not 1. Good. So the answer is 1 for when we plug in 0. What happens when we plug in 1? Very good. And when we plug in 2, obviously 4. Now, of course, we need the end behavior. We have never done this for any of the functions from before, but we will do it now. I'm going this way. 1, let's say 4, 2, 1, 1 over 2, 1 over 4, 1 over 8, 1 over 16, 1 over 32, 1 over 64, 1 over 125, 28. Where am I going? Towards? Thank you. Towards 0, of course. Of course, towards 0. Let's go to the other way, in the other direction. 1/4, 1/2, 1, 2, 4, 8, 16, 32, 60. Very good. We have never experienced this. We have never experienced a function with a horizontal asymptote at negative infinity only. We've never seen this before. As you see, there's no horizontal asymptote here. So now I'm ready to graph this function. Seems initially kind of weird. Can anyone give us the first ordered pair that we need to plot in order to graph this function? Right. First ordered pair, other than that. -2, 1/4, perfect. Next one. Good, next one. Next one. Good. This is the graph of 2 to the x. Of course, I don't want you to think that it stops here. Of course, it goes on forever and approaches 0. Getting closer and closer, closer and closer. I did not draw the horizontal asymptote because it's the x-axis. Otherwise, I would have presented a horizontal asymptote. What can you say about this function? And the answer is a lot. Madison, you wanted to say something?
Is it ever going to cross the x-axis? It's just getting really close.
Yep.
Forever.
Yep. It will not. We say eventually it may touch it, but no, not cross it. It's not possible. What can you say about this function? Again, I can say a lot. The domain is negative infinity to infinity. What is the range? Very good. 0 to infinity. Is it increasing or decreasing on all its domain? Very good. Everywhere. Great job. Is it 1 to 1? By the very good is 1 to 1. Does it have an inverse? If it's 1 to 1, of course, F inverse exists. Okay, I want to graph it. I know nothing about it. I don't even know its name, but I can graph it. When I graph both on the same coordinate system, what do I have to graph first? This is the simplest function that we graphed in chapter 2 before transformations, right? Y equals x. So now please give me a couple of points that I could plot and graph this function. Say it again.
1/4 negative 2.
Of course. 1/4 negative 2. Excellent. 1/4 negative 2. Here it is. Next one.
1/2
Excellent. 1/2. 1/2 negative 1. Very good. Next one.
1
Of course. Good enough. I'm happy with this. This is the inverse function of the given function to the x. And as expected, when I fold this graph, they have to overlap. Otherwise, they will not be inverses of each other. So here's a question now. The exponential function, you already told me, is defined on all real numbers and has range 0 to infinity. What about this function, f inverse? What is its domain? Of course, we know this. We know how the inverse function and the function work. Exactly. So do you think that this inverse function is what I call a friendly function?
For the most part, yeah.
Absolutely not. I don't like it.
No?
I don't like it. I have to worry about it. It's not defined everywhere. It's not a friendly function.
So that was a trick question.
It's like the square root of x. Why don't we like it? Because we have to write x equal to 0. Why don't we like 1 over x? Because we have to say x does not equal 0. So it's not a friendly function. Please remember that. Perfect. Excellent. Now let's look at some transformations. Let's say f of x equals -2 raised to x plus 1 and plus 4. We're asked to graph this function using transformations, but also determine the x and y intercepts algebraically. Use transformations to graph and find x and y intercepts algebraically. Use transformations to graph this function and find x and y intercepts algebraically. Okay, so base function, please. And no, you cannot say the square root of x. You cannot say the absolute value of x. You cannot say x squared. But you have to say,
It wouldn't be ax, would it?
but it would be 2.
Yes.
It will be 2 to the x. Indeed. That's the base function I used to create this. Indeed. Thank you. First transformation. And then the second, and then the third. First transformation.
Would it be the 2x plus 1?
Yes. Excellent. 2 raised to x plus 1. What does this do? Remember, yes. Remember, it's always a transformation can only be on the x-axis, on the y-axis. If I change x, it's on the x-axis. If I change y, it's on the y-axis. Very good. Left one. Next transformation is -2 to x plus 1. What does this do to number 1? Reflect. Yes. Reflect with respect to the x-axis. Excellent. And then -2 raised to x plus 1 plus 4. What does this do to 2? Because you understand number 1 and the base are all gone. Now this is a transformation. This is a transformation on to up 4. Very good. That's okay. Up 4. Now, what was the domain? We know it's all real numbers, but what was the range of the base function? If we omit all this, what would be the range of 2 to the x? 0 to infinity. But you understand that this function underwent some transformations.
So now the range changed.
Of course. So don't expect the range to still be 0 to infinity. It's not going to happen. Okay, so I'm graphing 2 to the x. Is it increasing or decreasing on all its domain? Yes, it is increasing on all its domain, and it has to cross at 0, 1. The base function, any exponential function, including this one, must cross the y-axis at 0, 1. Because when x is 0, y is 1. Then you told me to shift this one left 1. This is the only point I care about. I need to shift it to the left 1. Where will it land? Yes, at the same height. So this will be a -1, 1. Excellent. So this graph is the graph of 2 to x plus 1. Then you told me to reflect the graph of 2 to x plus 1. I need this point again. Where does it go? I'm reflecting this point with respect to the x-axis. Where does it go? Excellent. Excellent. Well done. So this is my graph of -2 to x plus 1. Great job. Now finally, what am I doing to the orange graph? I have to move what first? I did not mention it because all these three had the same horizontal asymptote, and that horizontal asymptote was the x-axis. But now when I move the graph up 4, where do I move the horizontal asymptote? Indeed, at 4. I have to move the horizontal asymptote first. So 1, 2, 3, 4. y equals 4 is the horizontal asymptote. Now, initially it was at 0. And now again, I need this point. Please tell me where will it land, and I'll construct the rest. Careful. 1, 2, 3, 4. Correct. So the point will land here at -1, 3. Do you all agree? Okay, very good. So now I'm going to graph the final function. So this is final. And it's y equals -2 to x plus 1 plus 4. Can anyone give us the range of this function? Do you remember when I was looking silly and I was doing this with x squared, blah, 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 and we were able to determine the range like this without even graphing it? Because we understood the graph and we could picture it. Okay. What do you think about the range of this function? But it stops at 4. Well, 4 is the horizontal asymptote. So from -infinity to 4. It cannot go beyond that.
No, it doesn't have a bracket.
Of course not. It's a horizontal asymptote.
Negative infinity be wrong.
I'm sorry?
Would 4 to negative infinity be wrong?
No, it's not wrong, but we normally read from negative values, from the small values to the larger values, always for the domain. Yes, do you want to say something?
Mm-hmm. No,
Okay.
I don't think so.
Is this clear?
Surprisingly.
Good. I'm happy. It's not a difficult function per se. I think polynomial and rationals are more difficult than this. Way more, right? Okay, so now we want to find the x and y intercepts algebraically. So let's find the y-intercept. How do I find the y-intercept? Let me write the function here one more time. I have it right here. So that equals -2 to x plus 1 plus 4. We have to find f of 0. Let's find f of 0 together. How much is 0 plus 1? How much is 2 to the first power? 2. How much is 2 times -1 in front? -2 plus 4. 2. So let's see how far was I. Well, it happened. It really happened by accident. I had no idea. I didn't calculate. So now I want to determine this. How do I determine that, which is the x-intercept? Yes, so I have to set f of x equal to 0, which is -2 raised to x plus 1 plus 4 equals 0. Maybe you've seen this before, but not in this course so far. It's an equation for sure, and I have to identify what it is. And you cannot say it's a radical equation. You cannot say it's quadratic. You cannot say it's polynomial. You cannot say it's quadratic in form. You cannot say rational. You cannot say any of the previous situations. But what is it? What is it? Of course, that's what we are studying, right? It's an exponential equation. Good. This is, congratulations, you are starting to solve your first exponential equation. Okay, first step. What do you think I'm going to do? Say it again. Yes, of course. -2 to x plus 1 equals -4. What do you think I'm going to do next? Now you know enough about me so far.
You're gonna multiply -1.
Of course, I don't want to deal with negatives, so I want only positives. Good. So now the next step you may need help with, so I'm here to help. I see on the left-hand side base 2. My very first thought is there a way of presenting this with a base 2? How? Very good. Excellent. Do not cross out bases. Do not simplify. At this point, we are only thinking. Yes, Garrett?
So why is it that when you multiply the -1, so the sign between x and 1 stays the same? Because you went from -2 to 2 and -4 to 4, but the x plus 1 stays.
Excellent question. So we have here -2 to x plus 1 equals -4. Okay, I'm going to change this into a. So I have -a equals -4. So what happens now? When I multiply both sides by -1.
You go to a equals 4.
Good. So now I'm changing back into 2 to x plus 1.
Okay.
I can't, if it's a very good question. If I have two terms and I have to distribute, it's a different story. But this is just one quantity. I cannot say monomial because it's not a monomial. It has, there's exponent is available. It's just one product, one quantity that I multiply by -1. I cannot just say, okay, let me multiply this and also this and this and this. I can't do that. It's just a simple quantity. You can replace it by any letter you want. When you multiply, you still have that letter. Very good question. Here's what we do next. We say this. Two numbers are equal and they have the same base. What has to happen to their exponents for them to be the same? Can I have here 4? No, because 2 to the 4th does not equal 2 squared. Can I have here -3? No, because 2 to -3 does not equal 2 squared. So x plus 1 must equal 2. If these two are not equal, then there is no solution. But they are equal because x is 1. So the x-intercept is 1, 0. I was kind of off somehow, but this is a little bit maybe. And this is 1, 0. So this is your first exponential equation. I would like us to look at some applications.
Okay.
Yes, go ahead.
No, it's not now. It's throwing me off a little bit.
Which part?
The I understand that it's just getting that x-intercept just looked weird. That's all.
Okay, but you
Probably
understand
just
it.
me.
You understand why you cannot distribute -1 to the power.
I'm just saying in general how when you're doing getting the x-intercept in general. That's all.
For this function or for any function?
For this one because of the.
It's your first exponent. I'm assuming it's your first exponential equation. We'll have plenty more. We'll have plenty more. By the end of the chapter, you're going to say more equations, and I'll say no. We're moving on to something else. Okay, I would like to look at the model will be given to you. So let's identify what this model represents. But let me write it first. A equals P. 1 plus lowercase r over lowercase n raised to n lowercase t. Of course, this is a product. When we say nt, it's n times t. So let's identify what these letters represent. A, the accumulated value. P stands for principal. You do not have to remember this model. It will be given to you in any problem. Principal. Lowercase r.
Is it the rate?
The annual interest rate, yes. Lowercase n is the number of times the interest is recalculated, but we use compounded per year. Lowercase n, I still have t, I know, but lowercase n is the number of times the interest is compounded per year. And lowercase t, time in years. Okay, when is this formula used? Let's suppose, here's the scenario. We want to put a down payment on the house of $50,000, let's say 5 years from now. We want to know how much money to deposit at a particular rate that is going to be given to us, this R. How much money we have to deposit today, keep it there for how many years, whatever, so that we can get at the end, let's say at the end of the 5 years, we have $50,000, we get it from the bank, and we go and buy a house. Here's another scenario. I want to borrow the money. I want to borrow the principal. I want to go to the bank today and say I need $50,000 for whatever, and I promise to pay it back in 10 years. How much will I end up paying per month? That's the accumulated value.
Yes. So
Because I'm borrowing 50,000, but they want, because I'm using their money, they want me to return not 50,000, but maybe 80,000 in 5 years or in 10 years, right? So it goes both ways. So here's our first question with this model. 54 on page 475. Find the accumulated value of an investment. I'm just going to copy the numbers and you'll tell me which one is what. For 10 years at an interest rate of 6.5%. If the money is compounded, part A, semi-annually, quarterly, monthly, and D, continuously. I'm going to copy the model here. 1 plus r over n raised to nt. And I would like us to identify what is given. Let me read the problem one more time. Find the accumulated value of an investment of 5,000 for 10 years at an interest rate of 6.5% per year if the money is compounded semi-annually, quarterly, monthly, and then continuously. Continuously means every second. And of course, this is not the formula. Here is the formula. I'll explain when we get to it. You don't have to even write it right now.
So with 5,000 would be
Yes?
the P.
Yes,
Right?
exactly. 5,000 is the principal. Well done.
10 years would be
Lowercase t. And this, which cannot be used, please make sure you are using 0.065.
would be
0.065
the lowercase r.
is the lowercase r indeed. So we correctly identified everything, not everything, right? We have to identify what semi-annually means, quarterly means, and monthly means. So the interest is compounded semi-annually. What does this mean? Yes, lowercase n is 2. Quarterly, n equals 4, and monthly,
12.
n equals 12. Because this is what changes in all of them, I'm going to create a function which is 5,000 in parentheses 1 plus 0.065 divided by x, because x will be 2 and then 4 and then 12. Why do I put x and not n? Because the calculator doesn't have n. And the power is 10x. T is 10 and n is x. So let's put it in the calculator. In y equals 5,000 in parentheses 1 plus 0.065 divided by x, close the parenthesis, power in parentheses 10x. Question, do we have to do this? No, you can just calculate the same thing 3 times. But this is a much easier way. You put the function in the calculator knowing that x is the only variable. It changes from 2 to 4 to 12. And you go to second and table, but I have to change this because it's every time. The system here at Rundle Mills has a what is called deep freeze. They cancel everything after I log out. Everything is gone. Okay, so we plug in 2 and enter, and then 4 and enter, and we plug in 12 and enter, and we get all the numbers without having to recalculate 3 times. You have to go and highlight the y values because we need the cents. So A of 2 is 9479.19. A of 4, scroll down to 4, A of 4, is 9527.6. 9527.79. And then the last one, 9560.92. A of 12, 9560.92. So the more times the interest is compounded per year, the higher the accumulated value. Of course, the difference is not that big because the amount is not huge. Yes?
I don't know what I'm doing wrong.
Let me take a look. So let's look at right. So let's look at what we entered. You've got the 1. So there is a 1. So enter 1 plus. And now when you're done, you can have
So there's another equation.
maybe not.
We need to get to that.
Oh, you didn't take it. The insertions.
How is the fossil formed
Now
after
it's
such and
yours.
such
Oops.
years, or how much carbon is in the air after such and such? So, you well, it's not as it's the same thing like this, but the equation's different. The only difference is you have to do something in your calculator with a lowercase e, but you'll do that with
got it. Thank you.
anyway.
Okay, any questions on this?
So isn't there, I don't know if I remember correctly, but I know there was one that I took in pre-calc where you use this to determine whether it's smart, if you earn more money by saving one way compared to another way. Aren't there ways
Yes.
to compare by
Yes,
using that?
we can find an example like that in which you will try to find the best way for you.
Yeah,
I'll find an example in a
well,
minute.
I remember doing that with this equation.
Yes, we will. In just 1 second, let's look at continuous. So the formula for continuous is this, but before that, I just would like to add one sentence. Special exponential functions. Special exponential functions. One is called common, and the other one is called natural. They both have base that is greater than 1. So here is the common, and here is the natural. So the common has base 10, and the natural has base e. And here's what I say, they are so special. Here it is. They have their own p in the graphing calculator right here. See, 10 to the x activated with a second, and here e to the x also activated with a second. So now we are ready to go and put in 5,000. Since this is just one calculation, I will not need to put in the in y equals, and I multiply by e second and natural log ln, and the power in parentheses 0.065 times 10. I'm going to write that down for you. I didn't write it on the paper, and then press enter. So A for continuous is 9577.70. So how did we get this again? We put 5,000 for the principal times e to 0.065 multiplied by 10. That's how we calculated it. The higher the base, the closer, all these functions that we've looked at, they all look like this. So this is the closest to the y-axis, so this will be 10 to the x. The next one, e to the x. This is e to the x. And the last one will be 2 to the x. Exaggerated, all of them. Okay, obviously they all have to go through 0, 1. And if you want to convince yourselves that as the base gets higher and higher, the function gets closer and closer to the y-axis. So I'm going to put them from smaller to large, small to large. 2 power x, the next one e to the x, which is the natural exponential function, and the last one common exponential function to the x. I didn't mean that. I meant this. Don't you start just yet. Okay, so we look at blue first, red second, black third. Ready? So I'm going to use the standard viewing window. Here it comes. Blue first is 2 to the x. Then the red, e to the x. Aha, closer. And now 10 to the x, even closer to the y-axis because its y values will be larger. So the larger the base, the closer it comes to the y-axis. Okay, very good. I would like also to look at a situation like page, oh yes, 56. Garrett had a wonderful idea, 56, on page 475. Let's read the problem. Suppose that you have $6,000 to invest. Which investment yields the greater return over 4 years? 8.25% compounded quarterly, or 8.3, is that what you had in mind? 8.3% compounded semi-annually.
That's the one you're comparing, which one's gonna.
Exactly. Very good. So we have two options. You're so patient with me, thank you. I'm sorry. Okay, so problem 56 on page 475. We have $6,000 to invest. We want to invest the money for 4 years, but we don't know which one is a better option for us. At 8.25% compounded quarterly, or at 8.3%, which appears to be bigger, semi-annual. We should not make a decision before we perform the calculations. I'm going to write the model. The model will be given to you. You do not have to memorize it. So here's the model. A equals P 1 plus R over N raised to NT. So what is given to us? What are these numbers? Very good. So this is the principal and this is the T. Very good. So now we also have this, which is 0.0825, which is the annual interest rate. And we have this, which is 0.083, which is also the annual interest rate. What is N here and what is N here? 4 and 2. Perfect. Now, for this, a lot of things change, so I'm not going to use a function. I'm just going to calculate twice. In the first calculation, I'm going to call it A1, is 6,000. 1 plus 0.0825 divided by 4 raised to 4 times 4. 4 times a year and times 4 years. So we'll get a number in a minute. And the other one, A2, is 6,000 and 1 plus 0.083 divided by 2 raised to 2 times 4 years. And we'll get a number. So we have to start from scratch twice because certain things change. Ready? Okay. Okay, so we have 6,000 in parentheses 1 plus 0.0825 divided by 4. Close the parenthesis, power in parentheses. 4 times 4, 16. What happened? How come? Thank you so much for paying attention. Oh, Thank you.
So I'm gonna delete the other one.
I say the other 4 is still there. You have 08254.
Oh, I see what I did. It didn't take the division symbol. Let me clear the whole thing. I see now. So 6,000 parentheses 1 plus 0.0825 divided by 4. Close power in parentheses 16 and press enter. Okay, I repeat the process, but this time I'm changing the numerator into 8.3. Divide by 4. I'm sorry, divide by 2. Close the parenthesis. And then the power. And the power is 8 this time. Is it? Yes. Good. And I got this. So option number 1 is A317.84. Option number 2 is A306.64. Even if you say, well, $11 is not such a big deal, but we're talking about long term. You may want to discuss this more than 4 years, and it makes a difference. So you will choose the first option, compounded quarterly, because the amount is slightly bigger. And with the interest, although the interest is a little bit smaller, but it's compounded larger number of times, double, as you see 2 and 4, and it gives us a better revenue. Very good. And I also would like to look at a problem like 866, and then we'll continue. 66, 75, same page. In 1986, explosion at the Chernobyl nuclear power plant in the former Soviet Union sent about 1,000 kilograms of radioactive cesium-137 into the atmosphere. So they're giving us a function f of x equals 1,000 times 0.5 raised to x divided by 30. Describes the amount f of x in kilograms of cesium-137 remaining in Chernobyl x years after 1986. So what is x for 1986? X years after 1986.
0.
Very good, awesome, thank you. If even 100 kilograms of cesium-137 remain in Chernobyl's atmosphere, the area is considered unsafe for human habitation. Find f of 80. What does f of 80 represent? Correct, 80 years from 1986, which is in 2066. So we want to tell these people who have their homes there, they were of course relocated, and whether they can go back home in 2066 if they are still alive then, or their families. Okay? So what do we have to do? What type of function is it?
Exponential.
It's exponential because the only variable is at the exponent level, so it must be exponential. All we have to do is just plug it in the calculator. We don't need it's just one number, so I don't need y equals. So clear. So we have 1,000 times 0.5 and the power in parentheses 80 divided by 30. If the answer is above 100, you will say to those people, and it happens to be 157.5 kilograms of cesium. Yes, it's 137 in atmosphere around the Chernobyl area. So what would you say? They should not go back. They should not go back, not even in 2066. As you see this model of the spread of the radioactive substance in the atmosphere of this town, Chernobyl, could have not been modeled with x squared, with the square root of x, with 1 over x, with x cubed, with any of that. It was modeled with an exponential function. So you will advise them not to go home.
What is that saying? Or what is that?
It's the name of the radioactive substance.
Oh, just a level of it.
Yeah, no, that's the name of the substance, the radioactive.
Yeah.
So 137, this is the name.
Oh, okay,
That's its name.
got it.
Cesium 137, that's the name. Okay, we have not looked at the other shape, however. We only know one shape for the exponential function with a base greater than 1. So let's look at the other one and then move on.
Where e is negative, right?
No,
Oh, that's
1/2 raised to the x when the base is smaller than 1. Let me look at the